What I thought I would do today, since there's undoubtedly many students in the audience and not all of you are familiar with surfactant-directed supramolecular assembly, I thought I would give you more of an overview rather than anything highly focused on what we're doing currently. But I'll allude to some of the things that are currently of interest in my group. So we'll focus somewhat on synthesis and then materials applications of these nanoporous materials. So here's the outline for my talk. Most of what I'll have to say is based on silica, and with the exception of a few examples on alumina, it's essentially silicate based. And I'll briefly show you some of the highlights that occurred early on in the historical development of this field on general supramolecular pathways. And then how these pathways affect the textural properties of the final products. And then most importantly, to show some representative materials applications. Although I don't believe that any of these are currently commercialized or in practice today, they will be, I think, in the very near future. And I'm personally making an effort to realize that outcome through industrial collaborations. And then finally, some discussion of crystalline oxides, because I think that's sort of the frontier right now in the area where we're learning to rationally engineer porosity into crystalline hosts as opposed to amorphous hosts. So let's begin with a micrograph of some representative mesoporous silicas. Now, is it possible to lower this light up here or not? Because the micrographs will show better. Yeah. That's the screen. This one here. Low light. Oh, it is low light, but you could maybe shut it off. Oh, it's too much.
That's too much.
Yeah.
That's
okay, I guess we'll have to live with it. But the first thing you see is that the pores in these structures are extremely uniform in size. And for the first two images, you see that the pores are very regularly ordered in space. The third image has, again, uniform pore sizes, but it's lacking this long-range order. And we call these wormhole structures. And I will show you examples of the pathways that lead to these highly ordered derivatives and the pathways that lead to these disordered wormhole structures. But what they all share, independent of the degree of order or disorder, is they have these incredibly uniform pores in the mesopore range and extremely high surface areas, never before realized for forms of silica, and incredibly high pore volumes. And so that distinguishes these porous particles from all other families of particles by virtue of them being mostly empty space. When you achieve a void volume of 3.5 cc's per gram with a silica, you're talking about 80% or more of the silica being empty space. And that's remarkable, to have a solid where you have that much accessible volume in which to do chemistry. So that's what they all share, and the way this field got started was in the publication in 1992 by a group of researchers at Mobil Corporation, and one of the team members happened to be a former graduate student from my group, and the discovery was actually a outcome of a side reaction that occurred in a reaction involving a surfactant and a layered silicate, namely a clay, and observed what has now become mesophase impurity to this reaction. And soon they discovered how to purify this side product to a very high degree, and that started this whole area known as surfactant templated mesostructures through molecular assembly processes. So basically, the idea was to generate surfactant micelles, which form at very low concentrations of surfactant molecules, to 10 to the minus third molar, for instance. Most of the surfactant is in micelle form. We draw it here as a rod, but most likely starts off as a sphere. But there are rod-like micelles known. And if you build the concentration of the surfactant to multimolar range, you will form what's called a liquid crystal. And liquid crystals were essentially the domain of, and their structures were essentially the domain of organic chemistry for many years. But what the Mobile group really understood was that this interface between the surfactant micelle and the solution was an arena in which you can do chemistry. And no one ever recognized that before. Although cationic surfactants, for instance, like CTAB, which some of you may be familiar with, always had a counterion to the hydrophilic head group that was inert chemically. They realized that if you put a reactive counterion at that, in this interface, it could undergo self-reaction, self-polymerization, for instance, and form a heterostructure in which you retain the micellar organization of the surfactant, but you coated the micelles with a second phase, in this case silica, and formed this type of heterostructure. And if it was sufficiently polymerized or cross-linked, you could then remove the surfactant, typically by burning it out, and be left with the skeleton of the heterostructure. And that started off a revolution of activity worldwide that's led to over 10,000 publications since 1992. So what excited, again, researchers was the fact that this combination of regular pores in the mesopore range, high surface area and high pore volumes. So it was a huge opportunity for chemical catalysis. And what Mobile was interested in was using these as catalysts for the refining of petroleum. In a good barrel of oil, only about 80% at best of the oil gets converted to useful products. The 20% of it ends up as tar, or the material you put on the street, to pave roads with, or for shingles on your roof. And that's a good barrel of oil. And if it's a lower grade barrel of oil, you make even more unusable tar. And so they were hoping they would have large enough pores to convert more of that tar to useful products. It turns out that the mesostructures that they made didn't survive the conditions of petroleum cracking. So they never really have made it in that application. But that's what drove these researchers to pursue this area of chemistry. And of course, other workers envisioned many other potential applications, and that's what generated all the worldwide activity. So that was the origin of it. What eventually then happened after the initial announcement is many people entered the field, and they realized that the type of structure that you get out, or the pore structure, the array, the three-dimensional array of pores, depended on what was called the surfactant packing parameter. So shown here schematically is a surfactant micelle with a polar head group that's wetted by the water phase. And this is the hydrophobe linkage or tail that self-aggregates to form a micelle. And the packing parameter is defined by this equation here. It's the absolute volume of the surfactant molecule divided by the volume that is necessary to enclose that surfactant micelle in a cylinder. Because the cross-sectional area times the length here is just the volume of a cylinder. So it's how far the molecule deviates from a cylindrical shape, basically, is what the surfactant parameter defines. So if the surfactant packing parameter is about a third, you have a great deal of curvature associated with the micelle, and that generates spheres, typically. If you start increasing it to a value of 1, if this is absolutely a cylindrical molecule, you'll get lamellar structures. And in between spheres and lamellar structures, you get these different ones, cubic, hexagonal, and so forth. So by playing with the geometry of the surfactant, you could affect different liquid crystal structures, and those were reflected again in the heterostructures that you made when you carried out a polymerization at the interface of the micelle. Well, that's basically how you could control structure. The way you could control size is simply by the size of the micelle, or adding a co-surfactant that could maybe swell the micelle. So you had control over structure as well as size of the pores. So here is the original MCM41 structure that was announced in 1992, and it's known now as famous MCM41. And I have indicated here that it was formed through what we call now an electrostatic assembly pathway. The surfactant was a cation, that is, the head group was a cation, and the inorganic reagent leading to the structure was an anion of silicate. It was a silicate anion. So what directed the assembly of the structure was this Coulombic interaction between the surfactant head group and the charge on the inorganic reagent. And as a result, this very long-range structure, hexagonal structure, was templated, assembled, if you like. And you can see the beautiful hexagonal symmetry here looking down the pores. And this particle behind it, you are looking orthogonal to the pores. And you can see the uniformity, how uniform the pores are all the way down the channels. And you can see that they're one-dimensional channels and not cross-linked. That is, there's no three-dimensional connection between the channels. So this is a purely one-dimensional system. So you get this beautiful long-range order that is really the consequence of what we call electrostatic assembly. In other words, a better way of maybe saying it is that if this is a surfactant micelle in this pore, it is interacting with adjacent surfactant micelles in adjacent pores through electrostatic interactions. In other words, the forces directing the structure are just like the forces directing the structure of sodium chloride. Yeah, it's the same long-range ionic forces that are operating here. So the fidelity of the structure is reflected in two ways, in the X-ray diffraction pattern and in the way nitrogen fills the pores. I'm going to give you an example of a diffraction pattern and then an example of a nitrogen adsorption isotherm. So here's the diffraction pattern of MCM41. Now, the walls of this structure are atomically disordered. None of the atoms, the silicon and the oxygen atoms, are on lattice points. So if you like, the SiO2 component that defines the walls of the pores are glass-like. They're not ordered atomically. Nevertheless, you see this beautiful diffraction pattern in the low angle region corresponding to very large d-spacings. This 100 is the order of 30 angstrom or 3 nanometer reflection. And this pattern is the result of the order of the pores themselves. And you know, when I first saw this, I was struck by it because it's the first example of an inorganic material that is formally amorphous, that is atomically disordered, but ordered on a length scale that gives rise to Bragg reflections. And inorganic chemistry never observed this before. Liquid crystal behavior was only observed in organic chemistry, but this is analogous to liquid crystal behavior. It's like having an inorganic micelle, if you like. It's the same basic concept. So you see the regularity of the pore network in the diffraction pattern, and you see the uniformity of the pore size in the nitrogen adsorption isotherm. And so what we're plotting here is nitrogen uptake as a function of the partial pressure of nitrogen at the boiling point of nitrogen. So if we had 1 atmosphere pressure in contact with the vessel in which this reaction is, this measurement is being carried out, you would fill the vessel with liquid nitrogen. So, but by keeping the partial pressure below atmospheric, you have partial pressures that over this entire range 0 to 1. So what is happening here is we outgas the pores so that they're empty, basically, of water and any other adsorbed species. And now we start letting nitrogen in and slowly build up the pressure. And what happens initially is the nitrogen molecules start binding to the walls of the pores, and eventually form a monolayer and multi-layers. And that's what's starting to happen as we increase the pressure. So up in this region, we're starting to decorate more and more layers of nitrogen on the walls of the pores. But then we get to a partial pressure where the film thickness on the walls become the order of the size of the pores themselves. And as that happens, the pores fill rather rapidly with liquid nitrogen. And once they're formed with liquid nitrogen, very little additional nitrogen is absorbed. In fact, we could say that once the pores are filled, the framework pores are filled, any additional uptake of nitrogen is due to filling of space between the particles of the silica. In other words, interparticle pores. Now, the fidelity of the pores is determined in large part, or reflected in large part, in the steepness of this step. The more regular the pores are, the more vertical this step will be. The more regular they are, the more spontaneous you will have pore filling. The larger the pores are, the more this step will shift to higher partial pressure. In other words, as the pore size increases, you need to put more driving force to force liquid formation in the pores. So diagnostically, just by looking at the adsorption isotherm, you immediately could get an idea of the relative pore size depending on where the step is located and how well ordered the pores are based on the vertical shape of that step. Okay? That's a very important thing to keep in mind. Because now I'm going to show you, well, one more thing. This is the fidelity of the pore size. There are different models that one can use to back out an apparent pore size depending on the shape of that step. Okay? And there's maybe a dozen different models that could be used to estimate what the pore size. And it depends on what the pore shape is, among other things like the composition of the walls and so forth. But without going into those details of what model we're fitting here, you could see that the apparent pore size, average pore size, is around 3 nanometers, and the width at half maximum here is the order of 1/4 of a nanometer. So we're talking about a 30 angstrom pore plus or minus 2.5 angstroms. That's remarkable fidelity to the pore structure. Okay, so now in about 1994, we got into the game by realizing that one of the downside of the mobile approach was the need to use a cationic surfactant to form a mesostructure. And the downside of that was if you wanted to get the surfactant out, you either had to ion exchange it out with protons, for instance, or some other cation, or you had to burn it out. And if you had burned it out, you had to destroy the surfactant. You couldn't recycle it. And doing an ion exchange reaction on the surfactant was not an easy thing to do. So what we had realized is that we could probably make these mesostructures using electrically neutral surfactants, like amines, some of which are shown here, or block copolymers, in which we have polyethylene oxide and polypropylene oxide segments, the ethylene oxide segments being hydrophilic, the propylene oxide segments being hydrophobic. And so these were electrically neutral surfactants that once you have the mesophase form, the heterostructure form, you could anticipate being able to solvent extract the surfactant from the pores and recycle it. And so, sure enough, we made a variety of mesostructures, but they almost always tend out either to be a wormhole structure, like I showed you on the first slide, or lamellar structures. We never observed hexagonal or higher order cubic structures. Now, but more recently, people have figured out that they can, in fact, use electrically neutral surfactants to get higher order structures, but that's another story. But we understand why we only make lamellar and wormhole structures typically, and that's because we're lacking that ionic interaction from micelle to micelle to help order the structure. So the hydrogen bonds that are involved in ordering the silica around the micelle only extend to that one little cavity of surfactant and silica. And the forces, the van der Waals forces, if you like, don't extend from one micelle chamber to the other. So you're stuck with either lamellar or wormhole structures. But nevertheless, they're extremely interesting materials. Now, in order to form a wormhole structure, you have to have curvature, right? It's easy to see how you would form a lamellar structure if the packing parameter is 1, right? The surfactant is a cylinder, so it lines up as a lipid-like or maybe a paraffin-like structure in the inner layer, and you generate between the lamellae of surfactant silica plates. Now, normally you wouldn't expect that to be interesting because if you remove the surfactant, the galleries would collapse and you wouldn't have any porosity. But what we discovered is that these lamellar materials are in fact porous, and the reason they're porous is the way in which we do the synthesis, which allows for silica spheres to be intercalated within that surfactant inner layer. So if you like, we pillar the silica slabs with local domains of silica. And so when the surfactant is pulled out, you actually have pores between the lamellae. And that's why you can have porous lamellar structures. But if you didn't have this pillaring effect, you would not have a mesophase, porous mesophase. Now, how do we explain the fact that you get wormhole structures with curvature and out of a mean surfactant, which on its own has a packing parameter of 1? And what we come to realize is that when you hydrolyze the silica in aqueous solution, the next thing that happens is that the silica associates with the head group of the surfactant, and depending on the extent of polymerization of the silica, this one shows a dimer, this is a tetramer, I believe, those pre-oligomers of silica hydrogen bond to the head group, and so instead of the surfactant acting as a packing parameter of 1, it acts as a surfactant with a packing parameter less than 1. Because you count not only the mean head group, but you count the hydrogen bonded precursor that's with it. So effectively that gives you curvature. And that's why you can make a wormhole structure. And as you could imagine, if you vary the degree of pre-hydrolysis in the synthesis, for instance, if you start setting up the hydrolysis of silica before you introduce the surfactant, you could vary the degree of curvature, vary the pore size. Okay, so that's how we got control over pore size and pore structure. So here's an electron micrograph of the same particle, but at 2 magnifications. And this is, again, the typical wormhole structure that was on the first slide. You can see every pore is uniform, more or less uniform, but there's no long-range order. The other important thing that the micrograph reveals is that the pores are connected. This is really a 3-dimensional structure, and a wormhole structure will always be 3-dimensional, which can be chemically an advantage. The other feature, which you see on the lower magnification image, is that the particles can be engineered to be intrinsically textured. That is, not only do you have the framework porosity generated by the surfactant, you have intrinsic to the particle these what we call textural pores, and they're also meso in size, that very much affect the accessibility of the framework structure. See, what's critical here, and I'll show you an example in a minute, of how access is so important in determining chemical usefulness of these structures. If we imagine, let's say, this being a catalyst with catalytic sites on the pore walls, the most likely factor affecting the reactivity of the catalyst is going to be the diffusion rate of the reactants into the catalyst. And so if there is reagents out here in solution that have to migrate through the pores, the diffusion length is determined by this local domain of framework structure. If this was a monolithic particle, the path length would be greatly extended, and that could have enormous chemical consequences, and I'll show you an example of that soon. We could also make wormholes that were monolithic in size. That is, without this intrinsic intraparticle textual porosity. And in this image on the right, you could see evidence for lamellar structures. You see here? These are layers here, and between the layers you have these pillaring effects, so that you generate pores. But locally there's lots of lamellar structure present. But then you'll see areas where there's no lamellar structure and it's wormhole-like. This is really a sort of a sample that express both the lamellar property as well as the wormhole property of a electrically neutral assembly reaction. So we focused for a long time on lamellar structures, mainly because they weren't so easy to make with electrostatic assembly. The electrically neutral assembly pathways were really very well suited for lamellar structures. So we could make some very elegant lamellar phases, and this was one of them, depending on the choice of surfactant. The surfactant in this case is what's called a Gemini surfactant. It has 2 amines in a head group, but that's a detail we don't have to be concerned with. I just want to emphasize here that lamellar structures are easy to make. And I have another one here. Now, what lamellar structures don't like to do is to stay lamellar, basically, because what happens at the edges of the lamellae is that the hydrophobic groups are in interaction with the aqueous phase, right? So the edges become thermodynamically undesirable. And so what will happen is the lamellae will fold on themselves to get rid of the edges and form a 3-dimensional hierarchical structure. And so on the left here, this is exactly what has happened. The lamellae have closed on themselves to form a vesicle. And so these are literally silica balloons, with the walls of the balloons being mesoporous. You can't see the mesoporous here because of the resolution, the low magnification. But you could see that the particles are empty. There's a huge void volume associated with that hierarchical structure. And these are examples of lamellae that have, again, closed on themselves into forming coiled slab-like structures. Another example is, I'm going to show you an example of this one in a catalytic reaction, what we call an onion-like structure. The lamellae have just simply coiled one around the other. Here's another example of the vesicle structure, but the vesicles being much smaller in that case. So that's sort of the textural properties of the framework and the hierarchical structure of these mesophases that are generated by electrically neutral amine surfactants. The black copolymers behave a lot like the amines, and we don't need to show many examples of that, but they're sort of parallel behavior. Now, if you look at the fidelity of the structure of a electrically neutral assembly pathway, the products that come out of such a pathway, you see a diffraction pattern that looks like this. Typically, it's one strong Bragg reflection and maybe a second weaker one. Many times the second one is not even present. So that's very different from what we saw with MCM41, where we had multiple Bragg reflections. And we see a isotherm that has the signature step for filling of a mesopore. And depending on whether or not we are dealing with monolithic particles or highly textured particles, we may or may not see a second uptake of nitrogen at very large pore sizes. But what you may notice here is there's the filling step is in about the same position as the one we saw with MCM41, meaning that the pores in this case are about the same size as the MCM41 structure. But what's different is the step is much more shallow. That is, it's not as vertical as an MCM41. And so that means that the pore size distribution is much broader here than it was in MCM41, but not a whole lot broader. Here is to remind you of what the MCM41 looked like. The diffraction pattern had multiple Bragg peaks, and the nitrogen uptake had a very sharp step. Now, what happened at about this point in time in the literature is my good friends and colleagues in the area started calling their material high quality. And so the implication was that a structure made by electrical neutral assembly pathways were low quality. And I had to give them an education about quality. Typical of chemists, they hate disorder. Anything that's disordered in chemistry is like hard to characterize. And so disorder is like low quality. To a physicist, they love disorder because it gives them opportunity to exercise all kinds of theories and do interesting physics, soft matter physics. But the chemical community thinks disorder is low quality. So I had to give them a lesson about that. And one of the ways I did that was with this image. This is a highly disordered piece of art. The image is very highly disordered. But you wouldn't call it low quality. I mean, most people would call this very high quality art. So quality has nothing to do with order disorder. And what really MCM41 is a highly ordered structure. And you know, an MSUH or whatever thing that was electrostatically, not electrostatically templated, is simply a disordered analog. But it doesn't mean that chemically it's of any lower quality. So I had to set off then to show chemical examples of that fact, okay? So I'll give you a few examples of how we showed that disorder is actually a chemical advantage. And this reaction we picked as to illustrate the point. It was actually used by Evelino Corma in Spain when he first demonstrated the catalytic application of MCM41. So we knew that MCM41 would catalyze this reaction. But what attracted me to it was the fact that all the partners in the reaction can react with a catalyst site all on its own, all by itself. You needed an acid site to get this product out. But if either reagent interacted alone with that catalyst site, it would undergo a dealkylation reaction. In other words, this T-butyl group would get clipped off. And you wouldn't want that to happen because you would not get the desired product. And the cinnamal alcohol would also undergo a condensation reaction at an acid site, form an ether. So you didn't want that to happen. That would be a distraction. And finally, once this molecule was formed, you had to get it away from the acid site rapidly before you prevent its dealkylation. So it's a perfect example to show where a reaction is going to be under diffusion control. The two reagents have to meet near the acid site, right? And as soon as the product is formed, it's got to get out of there and be replaced by more reagent. So we looked at the conversion of these two reagents over different acid catalysts, including MCM41, highly ordered, and a MSUG phase, which is highly disordered. Now, in all these reactions, the conversion was 100%. In other words, one or the other reagents reacted entirely. So there was either, typically it was a cinnamal alcohol that disappeared entirely from the reaction. So from the conversion of cinnamal alcohol, it was essentially 100% complete. So here are the results. If you use sulfuric acid and you do that reaction under homogeneous conditions, you can get about 10% yield of that product. If you use an acid clay, it was called K10, a flat surface, virtually every active site was available to each and every reagent and product. You got none of the desired product. Now, this is what Corma found. He found that if you make the system acidic by introducing some aluminum in place of silicon in the MCM41 structure, you got 31% yield of the product. Now, this is the MSUG material, which is layered and viscotic in its hierarchical particle morphology. You could do even better than MCM41. And the reason for that is the diffusion path is much shorter in these disordered structures than these more monolithic structures that are made through electrostatic assembly. So that was one example of such an advantage. And these are the comparison. This was the MCM41 catalyst, and this was the MSU G catalyst, where the diffusion length was decided by the very short path length of the mesopores. Normally, the way one would control a path length of a porous structure is to make the particles smaller and smaller. But if you make it too small, where you minimize diffusion, you start making colloidal particles that are impossible to recover in an easy way. But if you design in this hierarchical structure of textural porosity, you keep the same size of the particle, but you make local access to the framework far more facile. Okay, so another thing that the community at large is, I think, intrigued with is putting organic functionality on the walls of the pores. And typically the way you do this, well, there's two ways of doing it. The preferred way is to do it by what's called direct assembly, where you introduce the organofunctional silicate or precursor, siloxane, along with the typical TIOS, tetraethyl ortho silicate, that is the main framework reagent. And so as the polymerization occurs, the carbon silicon bond is very stable, and so the organol group is then integrated into the structure. And in this way, we've made structures in which half of the silicons are organically functionalized and half are just inorganic silica centers. So this is really the preferred way. And by the way, electrically neutral surfactant assembly is desired here, because now you want to get that surfactant out by solvent extraction. You can't burn the surfactant out here because you'll destroy your R groups. And this is another reason why amines and block copolymers are preferred for this kind of composition. The other way of doing it is to simply make a normal silica mesophase and then graft the silane to the walls of the structure. Am I still on or not? No, it just fell off, right? Here? Maybe my battery went out? Or maybe I shut it off. No, it's still on. I think the battery's out.
I've still got you.
Yeah, you got me on there, but the room is dead. I'll just yell louder.
Yeah.
Okay. Okay, so grafting is the other possibility. But this is preferred because you do it all in one pot and you get the reaction over with quickly. So by doing solid phase NMR spectroscopy, you could distinguish the organofunctional silicas, this is the so-called T sites, from the inorganic silica. So this is what you're interested in. In this case, it's a thiol functionality. And the Q sites are these ones that are lacking, that is the silicons lacking R groups, and the silicons are all linked to other oxygen atoms. And that's what the T and the Q designations is. But what's good about NMR is that you could, provided you do the NMR properly, you could integrate under these curves and actually determine the degree of functionality. So this is a system where you get to be 10% to 50% of the silicon centers are organofunctionalized with thiol groups. And so these are well suited for trapping of heavy metals like mercury. And I could show you an uptake curve. Now, unfortunately, my axes are reversed. This should be the mercury absorbed, and this axis should be the amount of mercury added. But the point is, this initial uptake is essentially a slope of 1. That is, what we put into the solution is what gets trapped on the trapping agent. Is it back to work? Okay, great. Yeah, good. So up to a 1-to-1 ratio of sulfur to mercury. And then there's some additional uptake beyond that, presumably because the mercury binds to silanol groups on the framework. And so we were very much interested in trying to figure out what the structure of the mercury was with regard to the sulfur atoms, and whether or not in this region the mercury was bonded exclusively to sulfur or whether oxygen hydroxyl groups participated in the binding. And it was likely that that oxygen was participating up here, but we weren't sure about what was going on down there. So one of the first things we did was XAFs in collaboration with an expert in the area, and you could find who he was, but he was very well. It wasn't Eric, by the way. He's an expert in XAFs. But this system was very tricky in XAFs, and we weren't able to really confirm. It looked like it was both oxygen and sulfur. It turned out that was not correct, and where we did end up with the correct resolution of the question was with pair distribution function analysis, which is shown on this curve, for which I am not an expert also. But I had a colleague in physics at Michigan State that was an expert in this form of spectroscopy. In fact, he was one of the founding fathers of it. And basically what this does is measure, even though the system is amorphous, atomically disordered, you measure scattering, which is a result of near neighbors, particularly heavy atom near neighbors, in the solid. So you could do this with totally amorphous materials. So what I've shown here is a series of PDF patterns. This is the one at the bottom is for the mesophase with just mercaptal groups, no mercury bonded to it. And you see the predominant peak is the one that corresponds to a silicon-oxygen bond. That distance is in agreement with a silicon-oxygen bond distance. And then the rest of them, all the other ones, have various levels of mercury bonded to the solid phase. And you see the other dominant peaks are a mercury-sulfur contact and a mercury-mercury contact. You don't see any evidence for a peak at a mercury-oxygen distance. And we had the standard references that had mercury-oxygen in the material. If there was mercury-oxygen in the material, we would see a peak in the PDF for that material. So we were pretty confident there were no mercury-oxygen contacts in the solid, and all the mercury was actually linked to the sulfur atoms. Now, we were also able to back out the number of sulfur atoms bonded per mercury, and at a 1-to-1 ratio, we kind of came up with this structure. You would see the mercury-sulfur distance and the mercury-mercury distance for this zigzag chain. And below, at a sulfur to mercury level of 2, that is, you were mercury deficient here, it was consistent with 4 sulfurs bonded to the mercury atom. And in fact, there are organometallic analogs of these structures, so we felt very comfortable with the fact that the PDF was giving us the right answer. All right, now more recently what we're up to is putting these nanoparticles, I call them nanoparticles, they're really several hundred nanometers in size. They're bigger than 100 nanometers, but typically less than a micron. So between 100 and 300 nanometers is a typical particle size of these materials. So we've been dispersing them in plastics with the idea of improving the properties of the plastic so that the amount of plastic you need to make a part, whether it's an automobile or a handle on this this laser pointer, you could use less of it. And the reason, environmentally speaking, that this is an important goal is that we use an incredible amount of plastic in our society. 30 million tons of plastic per year are dumped into landfills just in the United States alone. And we manufacture globally 250 million tons of plastic. So plastic really dominates our world. And most of that plastic, moreover, comes from petroleum. But there's now efforts to do biodegradable plastics or bio-derived plastics and so forth. So it's an important area. So our idea was, well, if we could strengthen a plastic or make it more durable in a way that would allow you to use less plastic in making a part, that would be a worthwhile use of these mesophases. So I'll just show you a few examples of some of our recent results. But before I get to that, the other thing about plastics, as marvelous as they are, they're hampered by certain negative properties. One of which is they're intrinsically weak. Most polymers are intrinsically weak. They need to be reinforced. The other thing is they need various kinds of additives to make them truly functional. And two of them, which are becoming of concern, are phthalates, which are plasticizers, like shown here, and polybrominated diphenyls or that are used as fire retardants. Neither one of these two molecules are desired in plastics because of their adverse effect on mammals, including humans. So they're endocrine disruptors, and there's all kinds of interest in getting them out of plastics. So our initial results show that the dispersion of just a few percent of the right mesophase, this is called MSUF, it doesn't really matter about its details, but the point is between 5 and 8% of dispersion of these nanoparticles, mesoporous particles, in low-density polyethylene or high-density polyethylene had rather dramatic results on improving the tensile strength and the modulus, or stiffness, of the material. So it's actually very difficult to improve both the stiffness of a polymer of plastic as well as its strength with one additive. Typically, you could always improve the stiffness by almost putting any particle in a plastic, calcium carbonate, glass fibers, whatever. But to improve both the stiffness and the strength is unusual. It's not an easy thing to do. So you could see at 8% loading, you could get 50% improvement in tensile strength and double the stiffness in a low-density polyethylene. And so, you know, in principle, you could anticipate using half the amount of plastic to make a part that required, you know, a certain strength and stiffness. So we have continued to pursue that, and it's one of the active areas in my lab right now. The other thing we found that certain composites will actually demonstrate improved durability through improved thermal stability. And this is an example with polymethyl methacrylate in which 5% of mesoporous silica was dispersed. We had actually several different ones. And you could see, depending on the porosity and textural properties of the particle, we improved the thermal stability of the parent matrix substantially. And this goes from 350 almost up to 400. Substantial thermal improvements. Now, the question is, why does that happen? In both cases, why do you get better mechanical strength and why do you get better thermal stability when you put in a mesoporous silica? And we believe, and this is our hypothesis up to now, I don't have any proof for it, but that when the polymer interacts with this porous particle, it actually penetrates the entire particle. And so the molecular weight of the polyolefin in this case is sufficient that a polymer strand can actually link one particle to another. And so you could conceive of a particle network formed through the entanglement of the polymer in the pores of the particle, whereas normal additives don't have porosity, and the only interfacial interaction is with the outside surface of the particle. And now, if that interface between the particle and the polymer extends over several tens or hundreds of nanometers, then the permeability of that interface could be affected and different from the bulk phase, and that would explain why oxygen is slower to diffuse into the structure and why you get better thermal stability. Now, everything I said to now, my hour is almost up. Yeah. No, I give you 5 minutes. Okay. Please give me 5 minutes, and I think I will end it. Everything I told you up to now has been amorphous. The mesophase has been amorphous. The big interest is in trying to get mesoporosity into crystalline materials for a variety of reasons. Electronic structures, catalysis, and so forth requires crystallinity. And so what we've been able to do recently is make mesoporous forms of alumina. And these are the micrographs illustrating them. We call them scaffold structures, or sometimes ordered scaffold structures. This one is more disordered than this one. But you could see that the mesoporosity are individual crystallites of crystalline alumina. And we know that they're crystalline from the diffraction pattern. This is the wide angle region of the diffraction pattern for the precursor, which in this case is boehmite. That's the precursor leading up to gamma alumina, which is this one here. And so this is the wide angle region showing that, in fact, the atoms are on lattice points and it's a crystalline material. And this is the low angle diffraction showing that, in fact, it is a mesostructure. That is, there's a sufficient correlation regularity between particles to give rise to a Bragg reflection at low angles. And you could anticipate that from these micrographs because the individual particles are more or less the same size. And that's why we're seeing this low angle diffraction. The other thing we've been trying to do is make mesoporous zeolites, and a lot of people are interested in this because zeolites are really very important catalysts in industry. And these are just a few structures of the more important ones. Faujazite, which is used in refining petroleum, MFI, which has got lots of different applications for small molecule chemistry, and its related derivative beta. But the way we set off initially to make a mesoporous form of a zeolite was by what we call nanocasting, or using what's called also a hard template. So the idea here is you have some solid template, not a surfactant anymore, but a solid phase that has regular porosity associated with it, and you fill those pores with the synthesis gel or precursor. You make the phase that you want in this host, and then once the phase that you want has been formed, you remove the host and you have the product, the desired product, in the same size as the original pores in your hard template. And the hard template we picked is called a colloid imprinted carbon, which was invented by Misek Jironiak at Kent State University. So this is, the way he made this is to disperse colloidal silica in pitch, carbonize the pitch to make carbon, and then dissolve out the silica colloid, leaving behind the colloid imprinted carbon. And so we came along and just filled these pores up with synthesis gel for the zeolite and made the nano-sized ZSM5 zeolite. Here are the micrographs of the templating carbon. This is the colloid imprinted carbon. So silica spheres of about 70 or 80 nanometers are used for this one. Down here, the silica spheres are the order of 12 nanometers. And when we crystallized the zeolite in these pores, you could see the beautiful regularity of the zeolite crystals. So they really do reflect, mirror the size of the hard template. We could skip this one. Now, the other thing we've been recently doing is trying to occlude a surfactant in a growing crystal. And again, the zeolite is the crystal here, but the idea is illustrated here. We want to somehow link a polymer to a growing crystal so that when the crystal actually propagates and grows in space, more and more polymer is incorporated or occluded into the crystal. And then once the crystallization is finished, we could burn out the porogen, and we would have then a crystalline mesophase. And the way we did that is to simply silate a polypropylene, polyethylene imine. I'll show you that in the next slide. Incorporated into the synthesis gel and forming what's called a proto-zeolite precursor, and then having the system crystallize. And in fact, it does work. And the way this was done was, again, taking polyethylene imine, epoxide functionalized silane, forming the linkage between the amine and epoxide group to, again, decorate the polymer with the silane. So you need this to have it incorporate into the silicate structure as the zeolite is growing. And sure enough, it forms the desired mesophase. What you're seeing here in the small dots are the framework pores of the zeolite. These are the order of a few angstroms, the order of, I don't know, five or so angstroms. What you see in the background, these very light phases, these light things here, are actually the mesopores where that porogen was present. And on the surface, you could see this region here. This region here is actually a pore that was occupied by the silica decorated porogen. Now, the chemical consequences of this could be important in something like petroleum refining. I won't go into this slide, let me skip it. But I was fortunate to have Kostas Triantafyllides, Greek guy. I feel sorry for a poor guy today, what's going on in Greece, but because he's at the University of Thessaloniki, a faculty member there, and I talked to him recently, and he's very troubled by what's going on in this country right now. Not only about the fact that his salary is going to be cut at least 10%, but the disruption that's going on over there. But anyway, I had the good fortune of having him in my lab, and he has access to a facility in Greece that is unique with regard to its ability to do petroleum cracking on a small scale, so that you don't need, tons of stuff or even pounds of stuff to test the catalyst. So he's got these microreactors that he's able to do real petroleum cracking on a few grams of material. Okay? So what I'm showing you here is the result of taking a mesoporous zeolite, ZSM5 in this case, putting real petroleum over it, and seeing what kind of products you get out. Okay? And comparing the mesoporous form of the zeolite with a non-mesoporous form of the zeolite to see if there's a difference in product distribution, particularly transportation fuels. Okay, so I won't go through all of it. But the blue line is the non-porous zeolite. The red and the green are the porous forms of the zeolite. So what you see is that the catalyst that has pores is much more reactive. It's clear because you've got more access to the acid sites that are doing the catalysis. So that was not unexpected. Gasoline is a very important product of petroleum cracking. What you see is that the mesoporous zeolites fall on the same line as the non-mesoporous zeolites. In other words, the selectivity towards gasoline is preserved in the mesoporous phase. The reason we can't make these two things overlap is because of the difference in reactivity. But if I extrapolate that line, the mesoporous zeolite is acting just like the non-mesoporous zeolite. So the framework pores are doing their work with regard to product selectivity. What is really different and exciting is that the amount of diesel fuel that you make can be substantially better with a mesoporous form of the zeolite than a non-mesoporous form. So if I extrapolate this out to the same conversion up here, let's say, it may intersect the red line, but it certainly is lower than the green line, which is a more mesoporous form of the zeolite. Now, it's only going from like 14% to 16%, but a 2% increase in diesel fuel is a huge improvement over in any petroleum refining process. We are getting more diesel fuel without compromising gasoline, which is to him a very important thing. The other thing we see with the mesoporous form of the zeolite is that it makes about the same amount of coke, well, in fact it makes less coke. Coke is a problem because it plugs pores. As you use the catalyst, you also form carbon in this cracking process, and it's a really messy reaction. You have to regenerate the catalyst, and so you don't want to make too much or excessive amount of carbon or coke. And so what you're seeing here is even though you have much higher conversions, the amount of coke can be even less than what you see in a non-mesoporous form of the zeolite. So there is some practical benefit to these engineered mesophases, and hopefully we will see commercialization of it in the near future. So I've covered approximately 15 years worth of effort in this area, and this is just a list of most of the people who have contributed. I think everybody who's made a contribution to what I said today is on this slide. And the guys with DR in front of their name were postdocs, and I should have put Eric with a prof in front of him, but I want to particularly point out Billings because he was the one that made possible this PDF technique for us. And the folks over here on the right are all graduate students that have gone on to their own careers, and some of them still working in mesophases, other than doing other things. But anyway, that's my story, and I thank you very much for the opportunity to tell it to you.
Thanks a lot, Tom. I think we can take more time for some questions. Maybe you can talk with Professor Pinnavaia after the lecture. Yeah.
John.
Why doesn't fidelity in an enzyme called organomercurial lyase? There is a way to convert alkyl mercury compounds to alkanes like methane and mercury. And I was looking at the structure of your thiol that is embedded in the construct that you have under a relatively, I guess, acidic environment. Have you ever tried an organomercurial to see how it would be processed in your system?
You mean to try and react the resulting mercury?
So an organomercury, it's say methyl mercury would actually go to methane plus
Yeah. No, we haven't done that. That would be a way to get the mercury back out. But actually, I failed to point out the way we can extract the mercury. The other thing I failed to point out, when you saturate this compound, this trapping agent with mercury, there's more mercury in the end product than there is silica. It's more than 50% mercury. And in fact, the trapping agent becomes a hazardous material. You couldn't possibly put it in a landfill. It would not be allowed. So you would have to extract the mercury and recycle it that way. But it is possible through just strong acid leaching, remove the mercury and return the trapping agent to the thiol state. So that's basically how we would do that, rather than the alternative. But that's an interesting way of maybe doing it. Yeah.
Very nice talk.
Yeah.
Just have a question about the nanocomposite system.
Yeah.
The pore size will be very, very small, and the polymer is very viscous. So,
Yeah.
so what is the capillary force in terms of penetrating those pores, and also the compatibility between the polymer which is hydrophilic and polymer which is hydrophobic?
Yeah. Those are critical questions, and I glossed over why all that's possible. So the compatibility of the particle for dispersion in the polymer depends critically on how many surface hydroxyl groups you have on the particle and how that matches with the polarity of the polymer matrix. So in a polyolefin, we really remove almost all, not all, but almost all of the hydroxyl groups. And we think that the hydroxyl groups that are left are buried in the wall. So they're really not accessible. Now, quartz is an extremely hydrophobic material. Most people don't know that, but it's actually hydrophobic. So siloxane bonds that are not protonated are actually hydrophobic. So, if you terminate a quartz crystal it's going to terminate in oxygen that eventually gets protonated because you're going to be breaking bonds. But if you cleave the quartz in an absence of air or moisture, it's a hydrophobic surface. So by reducing the hydroxyl group density on the surface, it makes the surface compatible with even a thermoplastic olefin. If you want to disperse it into a more polar polymer, it's okay to have, in fact it helps to have more hydroxyl groups on the surface. So we control that by calcination methods. It also turns out that the method of making the material has an effect on the accessibility of the hydroxyl groups and whether you have geminal or vicinal OH groups on the surface. So that also has an effect. With regard to your other point, how do we really know that the polymers link from, fill the pores and actually link from particle to particle, which we think it does? I don't have direct evidence for the thermoplastic system, the polyolefins, but I do for thermoset systems like the PMMA system, where we start with a monomer and then build the composite from that. And we also have done it with epoxies. And in that case, it's very easy to fill the pores because the pre-polymer is molecular. You could preload the silica, fill the pores, turn on the polymerization. And then in order to verify that, we have done in collaboration with David Gidley at the University of Michigan, positronium annihilation spectroscopy, which is very sensitive to porosity in the mesopore range. And so from that experiment, we find no evidence for any residual mesoporosity. So for thermoset, I'm convinced that the particles actually occupied, the pores of the particle are occupied by polymer. I have to do that same experiment with a thermoplastic. In any case, the viscosity always goes up. Whether you're talking about the viscosity of the pre-polymer in a thermoset, or you're talking about the melt viscosity of a thermoplastic, it always goes up. And I guess if you're really going to get exceptional mechanical benefits, you have to expect that. Yeah, but it goes up. And in fact, at loadings above 15%, the melt viscosity is so bad, it's almost not processable. So, but that's okay. We don't want to put, we don't want to get loadings typical of conventional fillers. We want to stay actually 5 or less %. Yeah. Yep.
Similar question. Is that better if we can use mesoporous carbon?
Yeah.
With a relatively larger pore size, 10 nanometers, to reinforce the strength of the polymer.
To use carbon?
Yeah, carbon.
Yeah, we have not done any mesoporous forms of carbon, but those colloid imprinted carbons might be interesting. We have not played with that system, but that would be a potentially interesting system for somebody like you to look at. Yeah, it'd be a good idea, I think. They're not graphitic, we know that, because we've done conductivity measurements on them, and we've done NMR, and we know they are not graphitic. So we actually tried very hard to make them graphitic. I had a visitor from Korea who was very interested in trying to make them graphitic, and we moved the conductivity in the right direction, but we really can't say that they're graphitic carbons. So, yeah.
Yeah, I would be, as you may imagine, interested in this alumina story. So you use oxide hydroxide as a precursor and form gamma alumina. If you increase or if you adjust the conditions to increase, say, the thickness of the wall, or maybe use another precursor, say aluminum hydroxide instead of aluminum oxohydroxide, would you see any changes in the phase?
We have used different precursors. I didn't point that out. We could use the aluminum esters, aluminum isopropoxide would be a typical one. We have used the aluminum 13 cation as a precursor. But the nature of the scaffold structure it does depend on the precursor, and I'm not exactly sure why, but it does. So yeah, we depend on having surfactant fill in the space between the nanocrystals of the precursor phase, in this case boehmite or the aluminum oxyhydroxide, and then we hope that we could convert that hydroxide phase into an oxide phase chemotopically, right? I mean, it's not a real isotopic conversion, but it's chemotopic. I mean, the morphology is staying fixed, lath-like or nano-sized, and as that transition of the hydroxy phase is occurring, there's enough surfactant to stay with the system to keep the pores open. See, if the surfactant vacated the composite before the dehydroxylation, we wouldn't form mesopores. So it's tricky to thermally process the system. You have to, you have to temperature program the whole process of dehydration, and while returning either the decomposition products of the porogen. I think sometimes we're actually making carbon, and it's carbon that's there that's actually ultimately responsible for the end mesopores, while we're forming the total, the gamma aluminum.
I see. But the alumina always remains gamma phase for different precursors?
Yeah.
Because they might be thermodynamically driven, I guess that's what I'm
Yeah. They're not nano enough to prevent corundum formation. If we take that scaffold structure and heat it to 1200, we form corundum.
Okay,
Yeah. So it's not like what you're seeing in your. They're not nano enough. Yeah.
I see.
Yeah.
Thank you. Yep.
I'm working on some micro older pore silicate. It's like with the cylinder with the MCM41.
Yeah.
But it's the pore size will be like 1 micron or 4 micron.
Yeah.
It's like older structure. I'm working on it for
Yeah.
like humidity sensing.
Uh-huh.
I'm just wondering, because now the limit of this structure is the pore size. The smallest we can get is 1 micron.
Yeah.
And that's because the lithography, the smallest structure we can get is 1 micron.
Yeah.
Is there a potential for this MCM41,
Yeah.
the application of this one into like the micro device, like micro sensors, like will be able to do micro fabrication on top of this?
People are actively investigating that area. I mean, I don't have any personal experience with that, but others are working on that. You're interested in biological or biosensing applications?
Yeah,
Or?
biosensing, or right now I'm doing humidity sensing, and you can do like gas sensing or like, it's
Yeah.
all you. But you need a device like capacitive or resistant device, so you need
Yeah.
to put some structure like
Right.
electrodes on top.
Yeah, people have, in the literature, you can go and go to SciFinder and put in MCM41 and then search that result with sensor, and you'll get a couple hundred hits. So people are using MCM41 for sensing application. I don't know if that answers your question, but people are using that either by just, making films, thin films, and there's some really interesting work going on in thin films. I think that's another frontier for this area, for the purpose of making sensors. Yeah.
So it's possible to make it like a uniform thin film with
Yeah.
a certain scale, like
Yeah.
dimension.
Yeah. There's some really good work by a guy named Sanchez from France, Clément, and he actually has made thin films of gamma alumina, very nice gamma alumina on Indian tin oxide. So you could look for that. You will find it. Yeah.
Okay, I think that you can join me to thank Professor Pinnavaia.
Yeah. Thank you very much.